Hello everyone, this is the first out of two videos on related rates problems that I'm going to make. And I emailed this to you. This sheet is designed to help you solve a related rate problem. So it says solving a related rates problem. And let me first tell you the problem that we're going to do, and then I'll go through how to use this. And I'm actually going to let you use this I'm going to email you guys this page, but I'm also going to have extras printed the day of your test so that when you do the related rates problem on your test, which is going to be a cone problem, which is not this video, but it'll be the next one, you could use this to help guide you if you would like to. So the first problem that we'll do is this one here. Okay, so I'll go like this so it's less busy looking. So water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? Okay, so first of all, I'm going to go through and I'm going to circle any words that tell me that I'm dealing with rates of change or derivatives. So water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate, okay, so there's my first rate, of 4 centimeters per minute. How fast? Whenever they're asking like how fast, that's also a rate. Okay, so how fast is the area of the pool increasing when the radius is 5 centimeters. The reason this is called a related rates problem is because we're dealing with two rates of change here. This is the rate of change of the radius of the pool, and they're asking about the rate of change of the area of the pool. And the area, this is a circular pool, so the area is pi r squared. So the area depends on the radius, so their rates of change are related, so hence related rates. Okay, now we're going to use, I decided to do this example, even though one like this won't be on your test, because it's pretty simple and it will give you an idea of how to approach these problems. So, A, draw a picture of the situation. Do not label the picture with any numbers yet. Guys, it's important that you follow these directions. I wasn't even going to present related rates problems to you like this, but I did last year with my students, and they really caught on quick. And I used this template, so if you follow it, you'll catch on really fast. So I'm going to do what it says, and I'm going to first draw a picture. I'm not going to label it with any numbers. To solve this problem, we need to write an equation. To figure out the equation, identify the concept from the box below that is relevant to this problem. Pythagorean theorem, area, surface area, volume, perimeter. These are the concepts that are gonna help you write a formula. Here we're dealing with area. Okay. Okay, so now let's write down the formula. So I've identified the concept. Now let me write down the relevant formula. So the area of a circle is pi r squared. Okay, and so that would be the radius there. Label the picture with any constant dimensions that were given. Never label your picture with a number unless it is a constant. Well, let's think about what's changing. Water is pouring down, and this pool is getting bigger. So these are the dimension I'm dealing with is the radius. The radius is changing. The area is changing. Nothing is constant. Okay, so and they're not giving me any constant numbers anyway. So I'm not going to label this picture with any numbers. But what I will do is I'll put an R there for the radius, which is changing. Okay, so labeled it. That was part C. Part D. Label the picture with the variables in the equation. Okay, I just did that. The charts below are intended to outline the logic involved in solving related rates problems. Fill them out. Okay, so possible rates. Guys, for this one, what I would tell my students, the possible rates that you will be working with are any rates of change. So, and you look at the variables of your equation. If the variable is changing over time, then its rate could come into play. Its rate of change could come into play. So is the area of this circle changing over time? Absolutely. So one rate that could come into play is A prime, okay, or dA over dt. All right, maybe off to the side I'll say dA over dt. I know using Leibniz notation was confusing some people, so I'm not going to use it. But you can use it if you'd like. What else is changing over time? The radius is changing over time, so r prime. Okay, that's another rate that could come into play. Now, what about known rates? What about rates that we know, rates of change that we know? The radius of the pool increases at a rate of 4 centimeters per minute. So we know r prime equals 4. Am I finding a rate? Yes. How fast, that's a rate, is the area of the pool increasing? Okay, so they're asking me to find A prime. And then at what moment, so another characteristic of a related rates problem is that you're finding something at a given moment in time. Okay, everything is changing over time, and they want to know if you could, stop time at just this one moment. What are the measurements of, what are the quantities of the stuff that's involved or changing? So at the moment when the radius is 5 centimeters, so at the moment when r equals 5. Now r is not always 5, it's changing, but they're interested in the rate of change of the area at this moment when the radius is 5 centimeters. Any other known values? No. If there are, you want to list them and then identify for yourself whether they're constant or not. Because if they're constant, this is important what I'm about to say, if you have constants, then you plug them in before taking the derivative. But if anything is not constant, for example, r equals 5, that is not constant, so I'm not going to substitute it in until after I've taken the derivative. Okay, so now we're on part F. Differentiate the equation or equations you wrote. And remember that every variable is a function of time, so you need to use implicit differentiation, which is basically the chain rule, on every variable. And then lastly, we will substitute where appropriate to solve the problem. Okay, so I'm going to use implicit differentiation here. The derivative of A is A prime equals, bring down the pi, that's just a constant multiple. Derivative of r squared is 2r r prime, because everything is implicit here, because everything is a function of time. So we're basically using chain rule. Alrighty, now at this point, guys, you might not find this necessary, but I think it might help, especially when we get to more complicated things. I'm going to rewrite this equation below, and I'm going to leave my rate to find, but everything else is going to get a blank underneath it, because I have to substitute in for everything else. So A prime, I'm just bringing down, I'll put the 2 in front of the pi, blank, blank. Okay. So you've got to substitute in for everything except what you're solving for. So what goes in for r? Well, we're looking for A prime at the moment when r equals 5. So 5 goes in for r. What goes in for r prime? That's the rate of change of r. And they told us that that was 4. And then just plug that into your calculator. And then my final answer is going to be this. When r equals 5 centimeters, A prime is equal to, and I already did this, so 125.6637. Now you got to be careful with your units. This is a rate, so it's going to be something over time. And area here is in centimeters squared. So area is two-dimensional, so it's centimeters squared, not just centimeters per minute. Okay? So there's that, guys. I'm about to do another video, a cone problem, which is more similar to what you'll see on the test. Okay, I will see you soon. Bye-bye.